All right, there's a video for lesson 5.5, Systems of Inequalities. Let's see, we have lots to get through in this lesson. The main topic is being able to graph the solution set to a system of inequalities. And then we're going to extend that into some applications. Now, this last learning target here isn't actually part of section 5.5 in the textbook. It comes at the end of chapter 5, called Focus on Modeling, starts on page 482. It is an application of systems of inequalities, which is why it's included in this lesson. So just be aware, it's not in, you wouldn't find those particular problems relating to linear programming in section 5.5. It comes at the end of chapter 5, starting on page 482. Before we get into systems of inequalities, we just need a brief review of linear inequalities and a quadratic inequality here. Primarily how to graph inequalities. If you recall from previous algebra courses, when you graph an inequality, whether it's linear or nonlinear, the graph itself could be dotted or solid, and then there's some shading which represents the solution set. So for example, this one here, y is greater than 2x plus 1. 2x plus 1 is linear, it's in slope-intercept form. So we have a y-intercept of 1 and a slope of 2, so up 2 over 1. And the inequality here is just greater than. If it had a greater than or equal to, then it would be a solid line. If it's just greater than, or if it's just less than, it's a dotted line. Since this is just greater than, I'm going to graph this with a dotted line. And then a big part of this graph is going to be the shading. The shading represents all of the points on the graph that would satisfy this inequality. Safest way to do this, whether it's linear or nonlinear, is to use a test point. So, for example, if the graph does not pass through the origin, which this one doesn't, I'm going to use the origin as a test point, the location of the origin being 0, 0. So I'm going to test the point 0, 0 for this inequality, which means x and y are both 0. If that ends up making a true statement, what that means is the test point I chose is in the shaded area because it satisfied the inequality. If I plug in a 0, 0 into this inequality and it turns out to be an untrue statement, then the test point I chose is not in the shaded area. So if I plug in a 0 for y, and then I plug in a 0 for x, 2 times 0 is 0, 0 plus 1 is 1, and it gives me a statement 0 is greater than 1. That's not true. 0 is not greater than 1, so my test point, which was right here, that test point did not satisfy the inequality, so it should not be part of the shaded region of the graph. What this tells me is the shaded region of the graph is above, away from the test point, so I would be shading above the line. So you are going to see quite a few graphs that are slope-intercept. If they're linear, slope-intercept. You will also see several graphs where it is still linear, like this one, but it's not a slope-intercept form. This is standard form, and quickest way I believe to graph these is by having 2 points. All you need is 2 points on a line just to graph a line. So if we have the X and Y intercept, then we can graph this line. So if we had a table of values here, if I let x equal 0, this is going to give me my y-intercept. If x is 0, then I'm solving the equation 3y equals 6, so then y equals 2. If I let y equal 0, then I solve the equation 2x equals 6, so x equals 3. So those are my x and y intercepts. So 0, 2, 3, 0. And before just graphing a line straight through them, you got to check the inequality. This is less than or equal to. Since it's an equal to inequality, I know it's going to be a solid line. Then I have to determine where to shade, so I'm going to do the same thing I did in the last problem. I'm going to choose a test point right here, 0, 0, and test. And test 0, 0, which means x and y are both going to equal 0. So if x here and y here are both 0, then I get 0 plus 0, which is 0. So that gives me a statement 0 is less than or equal to 6. That's true. That's a true statement. So what that tells me is the test point I've chosen is in the shaded area for this graph because it satisfies the inequality. So I'm shading toward the test point. Now we're not going to just be dealing with systems of linear inequalities. We're also going to be dealing with nonlinear graphs. This one right here, for example, is quadratic. And this -2 is outside the function. So it moves the parabola down 2 units. So the vertex is down here at 0, -2. There's my vertex. Now we need a couple of other points on the graph to have a better shape of the parabola, so I'm going to plug in a 1 for x. If I plug in a 1 for x, I get 1 minus 2, which is -1. And because of symmetry, I know that -1 is also there. Now, this is greater than or equal to. The equal to part means that I can graph this parabola with a solid line rather than a dotted line. If it was just greater than, I would have used a dotted line. Now we need to determine the shading, and as I've done with the previous 2 problems, the best way to determine shading is by using a test point. So I'm going to use this test point there of 0, 0 and see what kind of a statement I get. If it's a true statement, then I'm going to test the region that includes the test point, so I'm going to shade the region that includes the test point. If it turns out to give me a statement that's not true, I'm going to shade the region that does not include the test point. So if I plug in a 0 for y and x, I get a statement 0 is greater than or equal to -2. That's a true statement. 0 is greater than or equal to -2. So what that tells me is the test point is in the shaded region, which for this parabola is inside. I'm going to shading inside the parabola. Okay, so what we need to do now is pretty much the same thing we just did, except 2 inequalities are going to be graphed on the same graph, and we need to find the area of double shaded area. That's going to be the solution set, is the area that contains both of the shaded regions. So for example, we have a system of inequalities here. The directions are going to be find the solution set and then label all vertices. Vertices are the points of intersection of the 2 graphs, so not just the shaded region intersection, but where the actual graphs intersect. Those are called vertices. So for this one, we're just going to graph both graphs in the same graph. X minus y greater than 2. We'll start with this one. So since it's in standard form, honestly, the easiest way to graph this one is going to be finding the X and Y intercepts. So I want to make a list of points for graph 1. If I set x equal to 0, that's going to give me -y. And just to find points on a graph, I'm not going to use an inequality, I'm going to use an equation. So -y equals 2. Divide both sides by -1, and you get y equals -2. And then to find the x-intercept, you let y equal 0. So if I let y equal 0, then I have x equals 2 for that one. So 0, -2, and then 2, 0. And for this first inequality, since it's just greater than and not greater than or equal to, use a dotted line. And to decide where to shade, I'm going to use my test point right here of 0, 0. If I plug in a 0 for both x and y, then I get a statement 0 is greater than 2. 0 is not greater than 2, so my test point did not satisfy the inequality, which means the test point there is not in the shaded region. So I'm going to shade away from that test point, which would be below. Okay, for the second inequality, 2x plus y is less than or equal to 2. If I made a list of points here, if I wanted to find the x-intercept, I'm going to let y equal 0. So if I let y equal 0 here, then I have 2x equals 2, so x equals 1. And then if I want to find the y-intercept, I'll let x equal 0. If x is 0, then I have y equals 2. So we have 1, 0, 0, 2. And then since we have less than or equal to, the equal to part means we can have a solid line. Okay, let's try that again. And then to decide the shading, I'm going to use test point again, 0, 0. If both x and y are 0, then I have a statement 0 is less than or equal to 2. That's a true statement. So what that means is the test point is in the shaded area for this other inequality, so I'm going to shade towards the test point. So now the solution set would be the area on this graph that contains both of the shaded regions. So that would be this area right here. So I'm going to go ahead and make this area a little bit easier to tell. This would be the solution set right here. But then this set of direction right here, it labeled all vertices. The vertices are where the two graphs intersect. So I need to find the exact location of this point right here. And to find intersection points between two graphs, this is what we did in section 5.1 and 5.2 really. When we solve a system of equations, we're finding intersection points of graphs. So we need to have this system of inequalities, and change it to a system of equations. So x minus y equals 2 and 2x plus y equals 2. Now to solve this, it's nicely set up already to do a solution by elimination. So if we add these two equations together, then we have 3x equals 4. So x equals 4/3. And then if we take this and plug it in for that x and use that top equation, we can solve for y. So if I have 4/3 minus y equals 2, then subtract 4/3, then we have negative y equals 2 minus 4/3. Now subtract 2 minus 4/3. 2 is the same as 6/3. Now we can subtract since there's a common denominator, and we get the opposite of y equals 2/3. So y equals negative 2/3. So that vertex right there, the intersection of those two graphs, is the point 4/3, comma, negative 2/3. So just to keep track, there are two different things that we're finding here. The solution set is this. That's the area of the graph that contains both the shaded regions. And then the vertices would be boundary points of that solution set. So for example, right there, we have the intersection of those 2 points, or those 2 graphs rather. Now they may ask questions on the homework such as, is the solution set bounded or unbounded? This solution set right here would be an example of, let's get that back, unbounded, because the solution set just continues to grow and grow and grow. If I were to extend these 2 graphs out indefinitely, the solution set would just keep growing and growing and growing. So it's called unbounded. You'll see some examples here in a second where the solution set is bounded, meaning it won't grow any bigger than what's on the graph. We'll see an example of that a little bit later on. Okay, for part B, we have the system of inequalities with 4 inequalities. So we're going to approach it the same way we did the last one. I just want to address these bottom 2 because this is actually pretty common. X is greater than 0 and Y is greater than 0. If we wanted to look at that literally, X greater than 0, if I put a line right here at X equals 0, greater than 0 means anything over in this region. And then if I put a line for Y equals 0, this is the line representing Y equals 0. And then greater than 0 would be anything above that line. So just those 2 right there, those 2 inequalities, X is greater than or equal to 0 and Y is greater than or equal to 0, mean that the solution set is going to be right here in this top right corner of our graph. We call that quadrant 1. So it's just the fact that those 2 inequalities are there means when I graph this to find the solution set, I really only need to graph quadrant 1 and worry about quadrant 1 right here. So that's actually what I'm going to do. It's quadrant 1. Now, graph 1, if I wanted to find X and Y intercepts, if I want to find the Y-intercept, I let X equal 0. If X is 0 there for inequality 1, then I get 3Y equals 12, so Y equals 4. To find the X-intercept, I let Y equals 0. So if Y equals 0 right there, then I get X equals 12. So 0, 4, and 12, 0. And I have less than or equal to, you notice there, so that means those 2 points can be connected by a solid line instead of a dotted line. And notice I've only connected the points in the first quadrant, even though technically it does extend beyond that. Again, knowing that X and Y both have to be greater than or equal to 0, we only need to worry about the portion where X and Y are greater than 0, which is right there. Now, the second one, if I wanted to find the X and Y intercepts, if I want to find the X intercept, I let Y equal 0. If Y equals 0 right there, then I have X equals 8. If I want to find the if I want to find the Y-intercept, I let X equal 0. So if X equals 0, then I have Y equals 8. So that's my Y-intercept. And then 8, 0. And this is also a less than or equal to, so that means another solid line.
And then I've purposely left off the shading of both of these just to try to make this a little bit cleaner so I don't have so much shade happening everywhere. So let me go back to inequality number 1 to figure out where to shade. So this is this inequality here. We need to figure out the shading. I'm going to use a test point. The test point is going to be 0, 0. So if I plug in a 0 for both x and y, then I have 0 is less than or equal to 12. That's a true statement. So what that means is I'm shading on this black line here. I'm shading underneath towards that test point of 0, 0. So I'm actually just going to draw a little. You can do it this way just to keep track of where you're going to be shading. Sometimes it helps keep track so you don't have all the shade all over the whole graph. Now for the other one, for this inequality, you're going to do the same thing when you use it. I'm going to use a test point of 0, 0. If x and y are both 0, then I have a statement 0 is less than or equal to 8, which is true. So I'm also going to be shading towards the test point here on that red line. So I'm shading there. So the area that would contain both shaded regions would be this area right here. So there's the solution set. So that shaded region is the solution set. But then included in the solution set really would be vertices. So vertices are corner points or boundary points of the solution set. So we have one right here, one right here, one right here. So sometimes the vertices or the corners of the solution set are easy to identify. For example, that point is the origin, 0, 4, 8, 0. Other points like this one where it's the intersection of two graphs, as with the last example, you've got to solve it or find that point by solving a system of equations. And they're usually relatively easy. This one, especially when they're two linear inequalities, or linear equations in this case. If I multiply that bottom equation by -1, then x cancels. 3y minus y is 2y. Remember now that's a -8. So then 12 minus 8 is 4. So y equals 2. And if we take that bottom equation with y equals 2, and you can say now that x plus 2 equals 8. So x equals 6. So the location of that point is 6, 2. Now, one more thing. This would be an example of what's called a bounded solution set. The solution set is bounded by those vertices. It's not going to get any bigger. So that's bounded, whereas the last example, where was it? This would be called unbounded. All right. We have systems of nonlinear inequalities. So this could be, in this case, what we're graphing is a circle. If you have x squared, y squared, that's a circle. The way that you graph a circle, and they're going to keep it simple in this section. The center of the circle is always going to be at the origin. So really all you need to know is that the square root of that number is the radius. So in this case, this is a circle with radius 5. And then this one is just linear. So we have a line and a circle. So it is possible that the line goes right through the circle. You could have 2 intersection points. The line could be tangent. So if you have a circle and a line tangent to the circle, then you could have 1 intersection. But really, we're not just focusing on intersection points. Remember, we're focusing on solution set, which means the area that contains the shaded region, both the shaded regions. Okay, so graphing. For that first inequality, it's a circle with a radius of 5. The center of the circle is at the origin, so I just need to go over 5 on each axis. And since it's just less than and not less than or equal to, it needs to be a dotted graph. Now we're going to shade, and I'm not going to shade the whole thing. I'm going to just use little pointing arrows like with the last example. I'm going to figure out where to shade. It's either going to be inside the circle like this, or around the outer boundary of the circle. And the way that we can determine that, just like with all the others, I'm going to use a test point of 0, 0. If x and y are both 0 for that top inequality, then you get a statement that 0 is less than 25, which is true. It's a true statement. So the test point I chose is in the shaded area for that inequality. So that means I'm going to be shading inside the circle. Now for the linear inequality, let's see, change the color. Yeah, it's a pretty good one. Okay. Nope. There we go. And we're back to the... All right, we're experiencing technical difficulties here. There we go, got it. For that one, just going to make a quick table of values here for the second inequality. If I want to find the y-intercept, let x equal 0. If x is 0, then I have 2y equals 5. Divide by 2, and y equals 2.5. If I want to find the x-intercept, I let y equal 0. So if y equals 0, then I have x equals 5. So 5 comma 0, and then 0 comma 2.5. And since it's greater than or equal to, the equal to part means solid line. And then I need to determine the shading on this. So I'm going to use a test point right there of 0 comma 0. If x and y are both 0, then I have a statement 0 is greater than or equal to 5. 0 is not greater than or equal to 5. So I'm not going to be shading towards the test point in relation to this green line. I'm going to be shading away from the test point, which is in this direction. So the solution set, the area of the graph that contains both of those, would be this portion right here. That's my solution set. Above green line, inside the circle. Now, the vertices would be these two boundary points right here. And like I said, sometimes they're easy to identify. Like this one here, I know is going to be 5, 0. This one, not quite as easy. But to find intersection points of two graphs, remember the way that we do this is by solving a system of equations. So x squared plus y squared equals 25, and x plus 2y equals 5. Now, solving this kind of system of equations we talked about in section 5.4, solving nonlinear systems of equations. So if you're feeling a little unsure about how to proceed from here, then you need to look back at your notes in section 5.4, make sure you've done the homework. This one, we're not going to be able to solve by elimination. These are not like terms, so I can't eliminate those. And these are not like terms, so I can't eliminate those either. So what we need to do here is use substitution. I'm going to rearrange this bottom equation by subtracting 2y. So if x equals 5 minus 2y, then that also means that this x right here equals 5 minus 2y, so you make the substitution. And then solve the equation. This is going to result in a quadratic equation. This we need to simplify, multiply together using the distributive property. 5 minus 2y squared means 5 minus 2y multiplied by 5 minus 2y. So we're going to have 25 minus 20y plus 4y squared plus y squared equals 25. Add my like terms there. I have 25 minus 20y plus 5y squared equals 25. If I subtract 25 on both sides and just switch the place of those two, I want to write the quadratic term first. So I'm going to have 5y squared minus 20y equals 0. This is still a quadratic equation because we have a quadratic term. Your typical quadratic equation has 3 terms, and you can solve that by factoring or the quadratic formula. There's 2 terms here, both of which have common factors of 5y, and if we factor out the 5y, we're left with y minus 4, so the 2 solutions for y are y equals 0 and y equals 4. Now we need to find the corresponding x value for each of these, because remember what we're solving when we solve a system of equations are ordered pairs, which are intersection points, like right here, intersection points on a graph. So the fact that y equals 0 just tells me that y equals 0, I need to find the x coordinate, and then here, same thing, I know that y equals 4, I need to find the x coordinate. So for y equals 0, I'm going to use this equation and solve for x. So when y equals 0, right there, I'm left with x equals 5. So one of the points I already knew that one was 5, 0, but at least we were able to confirm it. And then for y equals 4, if I plug a 4 in there for that y, 2 times 4 is 8, so I have x plus 8 equals 5. Subtract 8, and I get x equals -3. So the other point there was the point -3, 4. So this much more involved, particularly this work right here of solving for those 2 vertices. But you've got to remember that when it says find the solution set and label all vertices, this is what it means. The solution set was this shaded region, and then the vertices were those 2 points. Okay, another one. These are both going to be quadratic inequalities. They're both parabolas. They're not really set up in a form right now that's very nice for graphing. So what I'm going to do is rewrite these and move the quadratic term over to the right. So if I did that, I'd have y is greater than negative 2x squared plus 4. And then if I did the same thing, if I move the quadratic term, I'm going to have the opposite of y is less than or equal to negative x squared plus 8. But I don't want to have that negative there. So if I divide everything by negative 1, remember when you divide by negative, you have to flip the direction of that inequality. So really what we end up with there is y is greater than or equal to positive x squared minus 8. So those are going to be my two graphs. Graph number 1 is a parabola that's moved 4 units up, but because of that minus sign, it's flipped upside down. So my vertex is 0, 4. And if I wanted to find a couple of other points there, I could let x equal 1. If x equals 1, then 1 squared is 1. 1 times negative 2 is negative 2. Negative 2 plus 4 is 2. So 1, 2. And then by symmetry, negative 1, 2. And since it's just greater than and not greater than or equal to, it's a dotted parabola. And the shading, I'm going to use a test point of 0, 0 to figure out where to shade. If x and y are both 0, I'm going to go back to the original form of the inequality right here. If x and y are both 0, then you end up with a statement 0 greater than 4. 0 is not greater than 4. So I'm not going to be shading towards my test point, which was 0, 0. I'm going to be shading away. So I'm shading on the outside of this parabola. Now the other one, the second inequality here, it's been moved down 8 units because of that minus 8. So 1, 2, 3, 4, 5, 6, 7, 8. So the vertex is right there. And then I want to find a couple of other points, so I'm going to let x equal 1. If x equals 1 right there, I get 1 squared, which is 1. 1 minus 8 is negative 7. So 1 comma negative 7, which also means negative 1 comma negative 7. And I need to extend okay. Now this one's less than or equal to, right over here, it's greater than or equal to. The equal to part in particular means that I can use a solid parabola. And then the shading, whoops, let me get the same color here. The shading, if I choose a test point, 0, 0, and let both x and y equal 0, then I end up with a statement that 0 is less than or equal to 8, which is true. 0 is less than or equal to 8. So for this red one, I'm going to be shading towards my test point, which is inside this parabola. So I'm shading inside So I need now to determine where the double shaded region and it looks like it's around the outside of that one in black, but inside the red. So it would continue like that. So this would be an example of unbounded. This is an unbounded solution set. Now what we're missing are the vertices right there. Those are found by solving a system of equations. And I'm going to go back to the original form of the inequalities and just change those into equations. So 2x squared plus y equals 4, and then x squared minus y equals 8. This is set up nicely for elimination because the y variables would eliminate, leaving 3x squared equals 12, x squared equals 4, and then if you square root both sides, you have x equals plus or minus 2. So remember, what that means though is we only have half. We have x value of 2 and an x value of negative 2, but we don't know the corresponding y values. So to solve for the y values, we use any one of these two original equations. So I'm going to use the top one and use this top one for x equals 2. Let's start with that one. For x equals 2, right here, if x equals 2, then you're going to have 2 squared, which is 4, and then 4 times 2 is 8. So 8 plus y equals 4. Subtract 8, and you get y equals negative 4. So for x equals positive 2, y equals negative 4. Now we've got to do the same thing for x equals negative 2. If I plug in a negative 2 right there for this x equals negative 2, then you square it and you get 4, and then 4 times the 2 here is 8. So we have 8 plus y equals 4, subtract 8, and we have y equals negative 4. So this one is the point 2 comma negative 4, and this one over here is the point negative 2 comma negative 4. Okay. Everyone's favorite thing. Applications. Some word problems. Just have to be willing to try your hardest on these. Not that I'm not saying that they're super challenging, but I'm also not going to claim that they're super simple either. You do, however, need to learn some of the skills here to solve these. And it's just going to take a little bit of patience and perseverance and being willing to be okay for a few minutes not knowing and then trying maybe some things that don't work and starting over and not getting frustrated, not giving up, just sticking with it. So there's a pretty good chance, since this is in section 5.5, that these application problems are going to involve systems of inequalities. More than likely, system of linear inequalities. And just a couple of vocabulary words. When it says, that's actually a typo, I apologize. That should say the feasible region. when it says graph the feasible region, that's just the same thing as find the solution set. Feasible region on an application problem is the solution set of a system of equations. Sorry, system of inequalities. So the first task is actually find a system of inequalities that describe the number of acres. And since we have a system of inequalities and we graph a system of inequalities, we're going to be finding a solution set, which is the feasible region. So first thing we do in any of the application problems we've done is identify the question, identify what's being asked. They're asking us to find a system of inequalities and then pretty much just find the solution set. Okay, so we know the question. Next thing is to assign variables. So we have a couple of different commodities here. It looks like we have cauliflower and cabbage. So they spell it out for us. It says find a system of inequalities that describe the number of acres of each crop that the farmer can plant. So we could let X be the number of acres of cauliflower, and we could let Y be the number of acres of cabbage. And just incidentally, this farm is probably going to go out of business because nobody eats cauliflower or cabbage, so it is a lost cause. But anyway, so we've got our variables. A difficult part sometimes after this step can be creating equations or inequalities using these variables. So we need to read through the rest of it now. It looks like there's two different things happening. There's planting and there's fertilizing. There's planting and there's fertilizing, so we may be able to make an inequality for planting, and then we could make an inequality for fertilizing. So let's first focus on planting. What does it say about planting? The farmer has $17,500 for planting. Planting 1 acre of cauliflower is $70 and 1 acre of cabbage is $35. So $70 per acre of cauliflower, and the acres of cauliflower I've said is X, so we could say that it costs $70 per acre of cauliflower and $35 per acre of cabbage, and this farmer only has $17,500. So adding those two values together has to be less than or equal to $17,500. Now we could do a similar thing for fertilizing. Fertilizer costs $25 per acre of cauliflower, so $25 times X, and then it's $55 per acre of cabbage, which is Y, and the farmer only has $12,000 there for fertilizing, so that's got to be, those two values added together has to be less than or equal to $12,000. And this next part is often overlooked, but it's something really important to keep in mind, especially when dealing with an application problem. The number of acres of cauliflower can't be a negative number, so just by default, X has to be greater than, I guess you could say, or equal to, if he's not going to plant any cauliflower, but at the very least, he's not going to plant negative acres of cauliflower. So x has to be greater than or equal to 0. And then same thing, the number of acres of cabbage also has to be non-zero, or at least not negative, non-negative. So I'm going to say that y has to be greater than or equal to 0. And we talked about that in an earlier problem. Really all that means that x and y are greater than 0 is that our graph, let's try this again, our graph is going to be contained within quadrant 1. And before we graph in the first quadrant there again, because of those, there's one more piece of information right here at the beginning, that there's only 300 available acres on which to plant. So the number of acres of cauliflower and cabbage together can't exceed 300 acres. So if I add the number of acres of cauliflower to the number of acres of cabbage, that's got to be less than or equal to the available number of acres, which is 300. So we've got one part of this problem done. We've got the system of inequalities. That's what was asked of us to do first, find a system of inequalities. Now it says find the feasible region, which really means graph the inequalities to find the solution set. So we need to graph both of these inequalities. So if we do this first one here, inequality number 1, since it's linear, we can just find the x and y intercepts. So if I want to find the x intercept, I let y equals 0. If y equals 0 there, then I have 70x equals 17,500, and then divide by 70. So now we go to a calculator, 1750 or 17,500, 17,500 divided by 70 equals 250. And then to find the y-intercept, let x equals 0. So if x is 0, then I have 35 equals 17,500. 17,500 divided by 35 equals 500. So if I went by 50s, for example, 50, 100, 150, 200, 250, 300, 100, 200, 300, 400, 500. So 0, 500, and then 250, 0. This is going to be a solid line because it's less than or equal to. And the shading, if I use this test point of 0, 0, and x and y are both 0 for this first inequality, then I have a statement 0 is less than 17,500, which is true. So I am going to be shading towards the test point. Okay, so for the second inequality, if I want to find the x-intercept, I let y equals 0. If y equals 0, then I have 25x equals 12,000. So 12,000 divided by 25 is 480. And then if I want to find the y-intercept, I let x equals 0. So if x equals 0 there, then I have 55y equals 12,000. So 12,000 divided by 55 equals about 218.2. 218.2. So 480, 0. It's right about there. And then 218 right about there. And this is going to be a solid line again. Let's try that again. And then a test point. I could do 0, 0. And if x and y are both 0, then I have 0 is less than or equal to 12,000, which is true. So I'm shading towards that test point as well. So it looks like the feasible region would be right in here. And last here but not least, this third inequality, x plus y is less than or equal to 300. We've got to graph that one. And for that one, the x and y intercepts are both just going to be 300. Right there. So if we kind of did that backwards, I apologize. If we let x equal 0, then y equals 300. If we let y equal 0, then x equals 300. There we go. And to figure out the test or the shade, we're going to do a test point. If x and y are both 0, then we have 0 is less than or equal to 300, which is true. So we're going to shade underneath that one as well. So the area that would contain all three of these shaded regions, let's see, underneath all three of them, looks like would be right here. It's our feasible region. Yeah, that's another typo. It's not 1.55. I'm looking at part B. Sorry, that should say 155. All right, so we finished part A, which is we found a system of inequalities. And the feasible region. Part B, can the farmer plant 155 acres of cauliflower on 115 acres of cabbage? Really what that means is x equals 155, y equals 115 in the feasible region. If it's not in the feasible region, it can't be done. Based on these constraints, that's actually what these are called. The feasible region is a set of constraints. If this point 155, 115 is not in the feasible region, then based on the constraints on this farmer, the availability of planting and fertilizing and available number of acreage, then it's not possible. So I've got to figure out, is that point in the feasible region? So 155 for X is about right here, and 115 for Y is about right here. So those two intersect right about there. So it's in the feasible region, which means that it should work. Now, depending on how accurately and how carefully you have drawn your graph, I'm just a little concerned. Let me zoom in here. I'm a little concerned. It's really close. It looks like it's in the feasible region, but it is really close to right there. That red inequality was this one. So I just got to make sure that it satisfies that red inequality. So I'm just going to double check 25 times X plus 55 times Y needs to be below 12,000. So 25 times 155 plus 55 times 115 needs to be below 12,000, and it is 10,200. So looks like we're good there. So I would say yes, that point's in the feasible region. So it is possible for this farmer to plant 155 acres cauliflower and 155 acres of cauliflower and 115 acres of cabbage. Okay. Last but not least, linear programming. Like I said, this isn't actually in section 5.5 of your textbook. It does have a lot to do with section 5.5, but it does start on page 482, which is at the end of chapter 5 in a section called Focus on Modeling. Modeling really is just a fancy way of a mathematical skill that involves taking data and creating an equation from the data. That's what modeling means. Or taking information and creating, in this case, a system of equations or inequalities. It's called modeling. So it's very, very similar to the problem that we just did, matter of fact, where we have to create a system of constraints or a system of inequalities, and from that find the feasible region. In essence, that's all linear programming is. So there's, again, an issue of vocabulary to be aware of. Linear programming will always start, or a major component is what's called the objective function. That's the objective function right there. And then right here we have what are called constraints. Constraints would be the system of inequalities. So using this setup here, our example is going to be find the values of X and Y that maximize P. And P refers to the objective function here. So find the values of X and Y that maximize P. So again, if you are familiar with what the vocabulary and what's being asked, this is not very much different than what we just did in the last example. The objective function is not graphed. You don't graph the objective function. What we do here is we're going to graph the solution set of the system of inequalities Second thing we're going to do is there we go. Find all the vertices of the solution set. Remember, vertices were the corner points of a bounded, in this case it's going to be a bounded solution set. Vertices would be the corners of that. Find all the vertices. And then the third thing is plug all vertices into the objective function to find max, in this case max, because they're asking us to maximize. If it said minimize, we would have done the minimum value, but to find the max value of P. So there really is only one additional step here, which is step 3. Step 1 and 2 we've been doing in this lesson for the last 3 or 4 examples. We're graphing a solution set, and then finding the vertices. We've done that before. So again, you do not graph the objective function. You're only going to be graphing what are called the constraints, or that system of inequalities. You notice that we have x and y are both greater than or equal to 0. So that tells us the graph is in the first quadrant. X is less than 10 is what I'm looking at now. Whenever you have an inequality, or an equation for that matter, that's just x, then that is a vertical line. So I'm going to count by twos here. 2, 4, 6, 8, 10. So I'm going to have a vertical line coming up through 10. And then x is less than 10 means this direction. This is where x is less than 10. This next one here, y is less than 20. Whenever you have an inequality or an equation where it's just a y equals a number, that's a horizontal line. So I'm going to count by twos, 4, 6, 8, 10, 12, 14, 16, 18, 20. There was 10. So 20, that's the line y equals 20. And y less than or equal to 20 means shading below. So I'm shading below that one. So far the feasible region is just that rectangle there, right inside here. So we've done that one, we've graphed that one. So now we're to this one. X plus y is greater than or equal to 5. X plus y is greater than or equal to 5. If I let x equal 0, then y equals 5. If I let y equal 0, then x equals 5. So the x and y intercepts for that one are both 5. And that's a solid line again. These are all solid lines because they're equal to and not just greater than or less than. Now for that one, if I let x and y equal 0 to find where I'm going to shade, then I have a statement 0 is greater than or equal to 5. 0 is not greater than or equal to 5, so I'm not shading towards the test point 0, 0. I'm be shading away from the test point. And finally here, x plus 2y equals 18, or less than or equal to 18. If I want to find the y-intercept, I'm going to let x equal 0. If x is 0, then 2y equals 18, y equals 9. So y equals 9 is right there. If I want to find the x-intercept, I let y equal 0, so x equals 18. Now to find the shaded region for that one, I'm going to use a test point of 0, 0, which means that x and y are both 0. So I would have the statement that 0 is less than 18, which is true. So I'm shading beneath that one towards the test point. Okay, a lot to keep track of here. To find the area that would contain all of the shade, I need to be below this line, above the x-axis. I need to be to the left of that line, x equals 10. Okay, so there is the solution set. I've done step one. Step one is graph the solution set. Step two, find all the vertices. The vertices are the corner points of the solution set. So I've got corner right there, corner right here, corner right here, one right here, and one right there. So I need to find all of those coordinates. Some of them are easy to find, like 10, 0. This one is 6, 0. This one here was 0, 5. That one there is 0, 9. This point, I know since it's on this line right here, that's the line representing x equals 10, so I know at least the x value of that point has to be x equals 10. I'm not 100% sure at this point of the y value, but I know that it's also the intersection of this inequality right here, which came from that inequality. So that line, if I want to change it into an equation, is x plus 2y equals 18. And I know that x equals 10 from right here. So if I plug in a 10 for x and solve by subtracting 10, get 2y equals 8. So y equals 4. So 10, 4. Okay, that satisfies step 2, which is finding all the vertices. Okay, step 3 is we have to plug in all of these vertices one at a time into the objective function, which is this right here. We need to plug in those x and y values into the objective function and see which one of those pairs of x and y gives the biggest value for p. So I'm going to plug in and find a value of p for the point 10, 4. I need to find a value of p for the point 10, 0. Let's see, what's another vertex? 6, 0. Let's see, 0, 5. And finally a value of p for 0, 9. Okay, and now all we do is plug in the x and y value there for this. So for 10, 4, it's 70 times 10 plus 82 times 4. For this one, it's 70 times 10 plus 82 times 0. For this one, it's 70 times 6 plus 82 times 0. This one is 70 times 0 plus 82 times 5, and this one is 70 times 0 plus 82 times 9. Okay. Let's do 70 times 10 plus 82 times 4. That's 1028. Then 70 times 10, and then 82 times 0 is just 0, so that's 700. 72 times 6, or 70 times 6 rather, it's 420. 70 times 0 is 0. 82 times 5 is 410. And then 70 times 0, and then 82 times 9 is 738. Okay, now they wanted us to find the value of x and y that maximizes p, so we need to find the max value of p, which is, that's the maximum value. So the value of x and y that maximized it, so we had x equals 10, y equals 4, maximizes p. So what this process actually is, we've spent the last 15 minutes doing linear programming, is it enables someone to take a lot of variables, and these variables are subject to constraints, and it helps one optimize large amounts of quantities so that there's not a lot of waste. For example, where it really was developed and became quite a useful mathematical concept is in army and logistics. If you think about mobilizing troops and supplies and everything else, there are a lot of different variables, there are a lot of different constraints on time and manpower and money and resources. And to keep everything running smoothly and to make sure that there is efficiency, you can set up what's called a linear programming model and find a feasible region, and you can either maximize or minimize depending on what it is you're doing. So here's a very small example where we only have two variables. It's really meant to do linear programming on a large scale with 20 or 30 variables, and you would use a computer to solve. But as just a small example, man, there's typos all over the place here. I should say two styles of shoe, Oxfords and loafers. In order to make these shoes, there's a cutting machine and a sewing machine. It takes 15 minutes on the cutting machine for each type of shoe, but the Oxfords have 10 minutes of sewing. Sewing, not serving. And loafers require 20 minutes of sewing. But then there's an availability issue because if there's only one operator, the process is just 8 hours a day for each machine. And then there's profit. Profit's $15 per Oxford and $20 per pair of loafers. The question is, how many pairs of each type should be produced per day for maximum profit? So there's really two different things being asked. How are we going to maximize profit, and how many pairs of each shoe should be produced in order to do that? So in linear programming, first thing we need is an objective function. What is the objective? And the objective really isn't just to find a number of pairs of shoes. The objective is to maximize profit. So I'm going to set that up as our objective. Maximize profit. Now, if we're going to assign variables, I'm going to let x be the number of pairs of Oxfords, and I'm going to let y be the number of pairs of loafers. And since my objective is profit, I'm going to say P for profit. It's $15 per pair of Oxfords plus $20 per pair of loafers. This is an equation that's going to describe profit. So there's my objective function. Remember, that is not graphed. That function there, we're going to plug in the vertices of the feasible region to see which one's going to give us our maximum profit. So we have the objective function. Now we need to set up and graph our constraints, or those inequalities. So the constraints x has to be greater than or equal to 0, y has to be greater than or equal to 0. We're not going to make a negative number of pairs of shoes. And then we can make an equation that describes cutting, not an equation, an inequality. We can make an inequality that describes sewing. And then we can make an inequality for, what do we want to call this? The amount of time, or what should we call this? Well, let's see. Each process is only available for just 8 hours per day. We can actually incorporate that into these two. So cutting each type of shoe is 15 minutes per pair for cutting. Okay, so here's where we need to be careful. I'm just looking at this. We have minutes, but then hours. We can't mix unit of measures of time. We can't have minutes and hours. So I'm going to put everything in terms of hours. So for cutting a pair of loafers is 15 minutes. That's a quarter of an hour. So I'm going to say 0.25. So it takes a quarter of an hour, or 15 minutes, to cut a pair of Oxfords. It also requires a quarter of an hour to cut a pair of loafers. And then the cutting process, it says each machine or each process is only available 8 hours a day. So it takes 25 or 0.25 or a quarter of an hour for cutting, and that whole process is only available up to but not exceeding 8 hours. So it needs to be less than or equal to 8. Now for sewing, let's see, Oxfords require 10 minutes. So 10 minutes out of an hour. So we need to put this in terms of an hour. So 10 divided by 60 is 1 divided by 6. So that's 1.66. You know what, I'm just going to leave that as a fraction, 1/6. And then 20 minutes of sewing for the loafers. So 20 out of 60 is 1/3. Again, that's going to be a nasty decimal, so I'm just going to leave that as 1/3. And then the sewing machine is also only available for 8 hours a day. Okay. So I think we have as many constraints as we need there. We have a constraint on cutting, we had a constraint on sewing, and then the natural constraints that x and y have to be greater than or equal to 0. So I think we're ready to graph the feasible region to find the vertices. Okay. So for this first one here, and you know what, for just the sake of ease, let's make everything into a fraction so it's all uniform. 1/4. There we go. So if I want to find the x-intercept, I'm going to let y equal 0. So if y equals 0, I have 1/4 equals 1/4 x rather equals 8. Multiply both sides by 4. Let's get that 1/4 y back in there. There we go. So it looked like x was equal to 32. When I had y equals 0, x was equal to 32. If I put a 0 in for x, then I have 1/4 y equals 8. Multiply both sides by 4, and you get y equals 32. So let's count by 5s. So 32 it's going to be solid. And then if x and y are both 0, I'm going to choose a test point there. If x and y are both 0, then I have the statement 0 is less than or equal to 8, which is true. So I'm shading towards a test point, which is down underneath that line. Now for the second inequality, if I want to find it, let's see, if I let y equal 0, then I have 1/6 x equals 8. If I multiply both sides by 6, I get x equals 48. If I let x equal 0, then I have 1/3 y equals 8. Multiply both sides by 3, and I get y equals 24. So 0, 24, and then 48 would be out here. It's another solid line. And then figure out the test point so I can have the right shading. I'm going to go x and y are both 0 for the point 0, 0, which gives me 0 is less than or equal to 8. That's also true, so I'm shading beneath that line. So the feasible region would be right here. So remember, step 1 is graphing the feasible region. Step 2 is locating the vertices. I've got one here, 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 and here. So that's the point 0, 0. This is the point 32, 0. That was a point 0, 24. That one there, since it's the intersection of two graphs, that one needs to be solved or found by solving a system of equations. I'm going to multiply this one by 4 to clear the fractions, and this one by 6 to clear the fractions. So then I get x plus y equals 32, and then x plus 2y equals 48. Now, let's see, you know what, I'm actually going to multiply this top one by -1. Multiply that top one by -1, add them together so that x eliminates. Remember, this is now negative y because I multiplied it by -1, so 2y minus y is y. This is now negative 32 because I multiplied it by -1, so 48 minus 32 is 16. So using this equation right here, x plus y equals 32. X plus y equals 32. If y equals 16, then x also must equal 16. So that's the point. 16 comes 16. Now what's left is step 3, plugging in each one of those coordinates into the objective function p to figure out the maximum profit. So the objective function, remember, p was $15 per pair of Oxfords, and I think it was, what, $20 per loafer. So for x equals 16 and y equals 16, this is going to be 15 times 16 plus 20 times 16. This one's going to be 15 times 32 plus 20 times 0. This one's going to be 15 times 0 plus 20 times 0, which we can already determine is going to be 0. The last one is 15 times 0 plus 20 times 24. Now before doing this, let me just go back and explain something real quick. What this feasible region means is this shoe manufacturing place can make, in this case, 32 Oxfords, 0 loafers, or 16 Oxfords and 16 loafers, or 0 Oxfords and 24 loafers, or it can't make anything. I guess 0, 0 would be nothing. But based on the availability of how much time it takes to cut and sew, that's the limitation. Any one of these would be a limitation, and we want to figure out which one of those maximizes the profit. Okay, so see if I can get that calculator up. 15 times 16 plus 20 times 16 is $560. $. 15 times 32, and then it's 20 times 0, so that's just 0. 15 times 32 is $480. We have $0, and then 20 times 24 is 480. So that's the maximum value of P. So to maximize P, they're going to make 16 Oxfords and 16 loafers.